All right, welcome back, my statics friends. In the last couple of videos, we've been talking about moments and particular scalar calculations as well as the basic formulations for vector forms of moments. And one of the calculations that we often find ourselves having to do is to determine what is the magnitude of a moment vector about some given axis. Now, this axis could be set up as a result of, maybe it's a shaft that's spinning and that's the axis is between the bearings, or we have a certain type of connection that is oriented in a certain way that I would be interested in knowing what's happening to the force effects on that particular axis. So finding results of moments on non-Cartesian axes is a very common trick. Now we'll show you how to do that in this particular video. So without further ado, let's get started. So here we're going to be looking at the moments of force about a line axis. Okay, now, as you recall, the basic form of this moment was r cross f. And so this is our formulation that we're going to use. Now, when we look for the moments of a force about a particular axis, what we're actually looking for is we're looking for a scalar magnitude. Okay, it won't be a vector, though I could just as easily build one based off of that component, but we're looking more for the scalar value, okay? And so we're going to manipulate that formulation that we had of m equals r cross f by just a little bit. So here's our basic moment that's calculated in space. And if you remember, if I take a unit vector and I dot it into another vector, I get the component along the line of that original unit vector. All right, so that's the game that we're going to play. We're going to take advantage of the same vector formulations you saw back with forces. We've talked about them a couple of times in the last couple of videos. It's the same game over and over because, again, at the end of the day, a moment is a vector. Okay, and so if I need a component in a given direction, I can take that moment vector and dot it into a unit vector and get the magnitude of the moment about that axis. All right, so, but if we kind of elaborate on this a little bit, I'll show you kind of the way this gets set up. So we know that for a given axis A, say maybe it's this picture here, we've got a three-dimensional Cartesian space. Okay, I have a force acting up here at this point. Now, in the last video, I showed you how to calculate the moment at O. Okay, but maybe we want to know exactly what's going on around relative to this axis. Okay, when we did it about O, we had an entire vector that came back. Okay, but if I want it about an axis, all I'm going to get is a magnitude. So it's a very subtle difference that happens there. Okay, now I may end up calculating the same moment at this point because this point O is on my axis line, but that may not always be the case. So the way that we set this up is I take my unit vector for the axis. And so that, as you know, will have an x component multiplied by an I vector plus a y component times a j vector plus a z component times a k vector, okay? And again, the magnitude of this guy has to be 1.0, and so these numbers are always going to be less than 1, like 0.8 or 0.62 or something like that, depending on the angles and the orientation of the line that you're looking at. Okay, and then I'm going to dot that into this 3 by 3 determinant, but you recognize this as just simply being the determinant operator on this cross product. So first row is I, j, k vectors. Second row will be the first term r. Okay, so rx, ry, rz are the x, y, and z components, and then the force vector is the second one, or in the bottom, and that will have components of fx, fy, and fz, those values. And again, these may be positive or negative. They can be zero. It depends on what's going on the particular force. But that's the basic operation that we're going to do. So it's a little bit lengthy. I mean, you've got a cross product, and then I got to dot it, following all the rules. So if you don't remember how to do those product operators, take a look back at one of the earlier videos we did. We actually went through dot products and cross products and have you take a look at those. So, all right, so let's give one a shot and see what we can do. Kind of the approach that we're looking at trying to figure out on this. So what I have is I have a force vector of minus 40I plus 20J plus 10K, and that's going to be in newtons. Remember our units. Okay, acting at a point A. Okay, now in this one, you can see that A is up here in space somewhere, and I have my origin established here at O, so that's my 0, 0, 0. And then what we're going to look at then is where is A located. So this A is located at a negative 3x, okay? It's a positive 4y, and it's a positive 6z above the origin, is the way we start to kind of look at that. So what we want to find on this is we want to compute the moment of force about both the x-axis and this OA axis. So this OA axis is the one that goes through a point that is -3 back and +4 over on the y. So it's this point is on the axis, and this OA axis is laying in the xy plane as we start to kind of look at that. Okay, all right, a little bit of lighting issues here. Let's move that a little bit, see if that helps. Okay, so first thing we have to do is we need to come up with a position vector that gets me from R from O to A. Okay, and so again, if this is 0, 0, then the coordinates of this guy will be the position vector. Okay, so that's going to be -3i plus 4j plus 6k. Okay, and then all I do to calculate the moment about the x-axis is I take a unit vector. So again, we're coming back up and I'm pulling this formula. So we want the x-axis. So this is the ux unit vector. And that axis is always positive I. Okay, and then I'm going to do r cross f on the rest. So that's all we're doing here. So that's where the positive I came from. And then I'm going to dot that into RA crossed into f vector. Okay, so I've gone through and I've done all the math, and like I say, for the sake of time, we'll move through this fairly quickly as far as this operation goes, but it's I dotted into the cross product. Okay, so you'll see I've got my I dotted into, and everything inside this parentheses is the result of evaluating the math on that. So if you do the math on this determinant, okay, you end up with a -80I minus 210J plus 100K, and that's all in Newton meters. Okay, so as you might expect, this means that I have a moment vector about the I-axis of -80I. I have a moment about the y-axis of -210J, and a moment about the z-axis of plus 100K. So these are vectors because they still have the unit vector notation on them. But if all I want is the magnitude about the x-axis, when I dot this guy, remember I dot I is 1, and I dot anything else is 0. So these last two terms will vanish, and so the magnitude of my moment about the x-axis is a -80 Newton meters. Okay, and the minus means that it's in the opposite direction to a positive I. Okay, so in this case we would write our magnitude with the negative sign on this thing, okay, in order to be able to evaluate that. Okay, all right, so now let's go through and let's look at, well, what do I do to find the moment about that OA vector? Okay, so again, we're going to look to be doing it about this line. Wow. Sorry about the light. We're going to try that. Okay, so we're looking at this OA vector here. Okay, and so what we need to do first off is that because we need, again, we're going back to our formula, I need a unit vector that tells me the direction of that axis. So we've got the Cartesian axes all figured out, ij's and k's, no problem. But this axis is a little bit different. So what I'm going to do is I'm going to establish a unit vector for OA. Okay, and you can see I've listed, I've got a UOA that would be acting along that line, and it has a length of 1. Okay, now I don't know what that is just yet, so I can construct it though. So what I'm going to do is I'm going to create a position vector from O to this point. Okay, and then I'm going to use that vector divided by its magnitude to produce the U vector that I need. And so that's the extra step that we're going to do. All right, so if we go along our line, our OA line, if you will, okay, slide that over a little bit, along our OA line, then this is going to be equal to a -3i, okay, plus 4j plus 0k will get me that value. Right? Because I went -3 in the x direction here, and I went +4 in the j direction, and I didn't go up at all in the z direction, so that's a 0. Okay, and so if I do the magnitude of ROA, position vector, then I'm going to take 3 squared is 9, plus 4 squared is 16, plus 0, so that's plus 25, and make the square root. I know that the magnitude of this guy is 5 meters. Okay. And so then when I construct my unit vector, it's simply this guy divided by this. All right, and if you look, that's what I have. I have -3/5 I plus 4/5 j, and that's my unit vector. Okay, so now when I go and I want to find the moment about the magnitude of the moment acting about that axis, okay, well, all I'm doing is UOA dotted into RA crossed into F. Okay, so this last piece is exactly the same as what we had before. That's this -80, -210, and plus 100 Newton meters on that, and I'm going to take that vector and simply dot it into this unit vector that we've created, 3/5 I plus 4/5 j, so forth and so on. All right, and so if I go through and I do that, then the only thing that remains is the I term multiplied by the I term plus the j term multiplied by the j term. So I'm going to do a minus 3/5 times a minus 80, okay, plus 4/5 times a minus 210. That's where all this is coming. So the first term evaluates to then a positive 48. The second term evaluates to a minus 168. And so this total is minus 120 Newton meters. And that is the magnitude of the moment about that axis. So that's all we've done. It's not too hard. It's just kind of taking these vector operations and going one step further, but kind of thinking about it in a different direction, or a different sense, if you will. Now remember, whenever we take the moment about an axis, we're getting a magnitude, not a vector. Okay, whereas if I do just r cross f, that gets me a vector. So a vector dotted into a vector gets you that scalar that you're wanting. So that's kind of the formulation that we're looking at doing on that. All right, so let's try another one. And I'm going to kind of, this is a rework of a homework problem out of an older version of Beer and Johnson. It was 357. I think it's out of the 10th or 11th edition, but it's kind of, it illustrates a point that we kind of brought up in the last video, but also kind of what we can do in this one. And so I thought it would be worth revisiting this one. So what I have is I have a shaft that is pinned at A and pinned at B, okay, with a single rod, and then it has this elevator arm, CD, located somewhere in the middle, okay? And so if you look at this particular piece, now there's a force F up at the top of this shaft that's acting on a line that goes down through G. Okay, now in the original picture, there was a lot of coordinate data that was produced on this, and so I didn't, just to keep the drawing somewhat clean, I have the coordinates of A, B, C, D, and G here. Okay, all right, and so everything in this, so I think this was, probably, I think this was pounds. Okay, and then maybe these are inches. Okay, and all of those would be units of inches. I've been pretty sloppy on the units. I apologize for that. Okay, so here's inches like that. Okay, and so those would be the locations relative to an origin somewhere. The origin would have been like out here or something. Okay, somewhere at that location. And so all of these, if this is 0, 0, then these are the positions of all of those other points on there. All right, so the things that we need to be able to compute this, okay, what we're being asked to find is we want to find the MC vector at that location. So we want to find the moment about C of whatever's happening by this force. Okay, so to do that, we know that there is a couple of different ways that I can calculate this, right? The first one is I can do MC. So again, we're going to watch our subscripts here, that these have to match. Okay, and so maybe I use point D as my point. And this one's fairly convenient because I have the coordinate of it. And so I could just do this force vector. So this would be F acting at D. All right, and so that's what I'm doing down here. Okay, and so if I do I, J, K, and this is just my cross product operator again, okay, the RCD that we find for these points then would be coordinate D minus coordinate C for the IJs and Ks. So I would take this D minus this C. Okay, so minus 16 gets me a 0I. Okay, and then I have 38 minus 15 gets me positive 23, and then I do 12 minus 12 gets me 0. So this is a very friendly vector. It's only, you know, in the single y direction, you know, 23j inches acting up. All right, and so then RCB, so with that, that's my vector 0, 23, 0. If I come back down to my calculation, here's the 0, 23, 0 here. So that's my R, because remember, R is on the first column, F is on the second. Because R is first here, F is on the second. And then I plug in my F values, 105 minus 190 plus 90. And if I evaluate this 3 by 3 determinant, and again, if you need help with this, go back and review the cross product operation. But by now, you guys should know how to do this. All right, the math comes out to be 2070 I plus 0j minus 2415 k, and that's pound inches on that. And that would be the vector here. Now, if you remember, we said that when doing a moment vector, okay, the R didn't matter as long as I went and found a vector that was somewhere on the line of action of the force. I chose D because it's convenient, and a lot of times I'll choose the one that gets me the simplest position vector that I need. Okay, but sometimes that's not the case. All right, so here's a D, but if this vector, force vector, is acting on a line that goes from D to G, which is this dotted line, okay, remember forces are sliding vectors, so I could pick him up and I could slide him down and have him acting down here at FG. Okay, and then so all I would need then to find the moment at C is a vector that gets me from C to G, crossed into then my force acting at G. It would be the same vector, it's just now in a new position on its line. Okay, and I can go to any point that I want. And a lot of times, there will be, support locations or something that will make this convenient to be able to calculate. All right, so if I go through and I do that, let's try it. So the first thing we got to do is we got to find RCG. Okay, and so just like we did before, so my head is at G, and again, we're doing our labels such that if I write this out, I want the moment at C, my force is at G, the subscripts have to match. C and C and G, those have to match. Okay, so I know I need the vector RCG. And so if I look at C, and this is G, that's RCG. The head is down here pointing at G. So when I go and find my position vector, it's going to be G minus C. It's head minus tail. Okay, so if I do that, I'm going to take G minus C, and that's going to get me plus 21I minus 15J plus 18K, and those are all in inches. Okay, and so then I can go through and do my calculation just for posterity. And notice all the numbers are different, especially on that center row on the R line. The forces are all still the same because I just slid it to a new position. But I plug in my R component, so that's plus 21 minus 15 plus 18. That's what we saw up here in RCG. Okay, and then I plug in my forces. Those are the same as before. And if I do the math on this and evaluate it, what I get is plus 2070I plus 0J minus 2415K pound inches. And if you look, it's exactly the same for both. Okay, and so that's the trick. So pick this. So the thing that we like about the moment equation is that I can choose the point that I choose to sum moments at, or choose the point where the forces are applied. And so I can choose one that's simpler. This is a whole lot more complex to calculate than this one, okay, because all these zeros are to kill off a lot of the terms in my determinant. Okay, so this would be easier to compute, so maybe I would choose this one to work off of, but I can do it in the longer method on that. So that's kind of an interesting little illustration I wanted to kind of bring back and illustrate what we can do with these vectors for calculating moments. Now again, we talked about this a little bit in the last video, but didn't actually work an example illustrating or proving it, so that's why I wanted to show that to you as well. Okay, so now let's say that we want to find, so we wanted to find the moment at C, so that's done. Maybe we want to find the magnitude of the moment, okay, about the line ABC. So this is the axis problem that we're working on now. Okay. All right, so the way that I would do that, then I need a position vector or some unit vector, again, that defines this line A to B. Okay, and we're assuming A, C, B are all in a line. And so I can come in and I can we'll show you how to do that. Now again, we're going to take advantage of our coordinates. So if you remember our A, B's, and C coordinates here, if you've got the note packet, this will be easy, but if you're watching the video, you may have to jot these down or pause it and to be able to see where the numbers are coming from as we work the next example. All right, so let's go through and let's look at the projection of MC onto line ABC. All right, so R from A to B, again, we're going to take from A to B. So the head is at B, the tail is at A, so I'm doing B minus A on our dimensions. All right, so I'm going to take my B, which is taken at 0, 0, 0, that's convenient, okay. And then I'm going to subtract off all of my A stuff, and I'm going from A to B, so I'm drawing a vector that's going this way. It's going this way right here, okay? All right, so that's what we're working at on that one. All right, so then RAB then is plus 32I minus 30J minus 24K. It's the same game we've been playing. Come up with a position vector in inches. And then once I have that, I can find the magnitude. And again, that's just squaring all of these terms, adding together and square rooting. So that's 50. Okay, and from that, I can build the unit vector. And so all it is it's this R over its magnitude, and it's 32 over 50I minus 30 over 50J minus 24 over 50K. And if I simplify that to two decimal places, it's 0.64I minus 0.60J minus 0.48K. Okay, and if I go through and test the magnitude of this, squaring all this and square rooting, you'll find that this is about 1.0. So this is a valid unit vector. All right, so then to find the component of the force acting on that line, I take that unit vector and I dot it into my moment vector. Okay, so I'm going to take all of this. So anything with an I gets multiplied by an I value in the moment, and anything with a j gets multiplied by a j value in the moment. So let's go pull back our vector again. Put this up here where we can kind of see what's going on. So our moment vector is this guy here, plus 2070i plus 0j plus 2415k. Or sorry, a negative. There's a negative sign in front of there. Got to watch the negative signs on this. All right, so if I take my unit vector, which was the 0.64, I'm going to take, because the i's go together, so I got 0.64 times 2070, so I'm taking this value times that value, okay, and then I'm adding a negative 0.6 multiplied by 0, and then adding a negative 0.48 times minus 2415. So that's everything that you see in this line, okay, and that will get you the magnitude of the moment about ABC. Okay, because I'm doing a unit vector dotted into a moment vector. So if I do the math on this, the magnitude of the moment is 2184 pound inches, or sorry, 2484 pound inches. And if I want to convert that to pound feet, which is a common practice in engineering, is 1 foot over 12 inches, this becomes 207 pound feet. Okay, and so this was just an alternative way to show how to do this process. Solving it, and then the answer in the back of the book was 207, so it matched, and that's all this was saying. So I wanted to kind of illustrate some different skill sets that can come out of this. This is a very good problem as far as understanding what you can do and how to find things. This is a real good quiz problem or a test problem, so if you're one of my students, pay attention to this one. That's your hint for the first test. So anyway, that being said, it won't be that exact problem, but those skills, you'll notice it's the same steps over and over and over, and that's what I'm after trying to see. So anyway, I hope that's made sense. If you've got any questions, as always, leave us some comments down below. Otherwise, give us a like and subscribe to the channel, and we'll keep the videos coming. So have a wonderful evening, and we'll see you guys next time. Happy engineering.